Very good morning to one and all. Myself, T. Muthukumar, Assistant Professor, Department of EEE, Kongunadu College of Engineering and Technology. Today, I am going to deliver a lecture on basics of electromagnetic fields. So, in electromagnetic fields subject. So, first of all, what is mean by electromagnetic field? So, electromagnetic field is a combination of electric field and magnetic field. So, it is called electromagnetic field. So, it is a physical field produced by electrically charged particles. So, this field is the combination of electric and magnetic field. So, it is one of the branch of physics of electrical engineering in which electric and magnetic phenomena are studied. So, basically two charges. One is charges at a rest position, charges at a moving position. So, the electric field is produced by stationary charges, that is charges at in rest position produces the electric field. So if you place the point charge, so around the point charge some particular region, some electric field will be available, so some effort will be available, that is called electric field. So magnetic field is produced by moving charge, so current flowing through a conductor, so produces a magnetic field. So it is the combination of electric field and a magnetic field. So next one is electromagnetic wave. So one of the important parameter in electromagnetic fields, electromagnetic wave. So it is the combination of electric wave and magnetic wave. So both are perpendicular to each other. So in blue lines, so blue waveform shows the electric field. So this is electric field E. So this is magnetic field and shows the red color waveform. So both are perpendicular to each other. So two important parameters for electromagnetic waves. So one is wavelength, another one is frequency. So depends upon frequency and wavelength. It has some more saves less energy or more energy. So next one is applications of or different types of electromagnetic waves. So under the electromagnetic spectrum, so electromagnetic waves classified based on the frequency and wavelength in different types. So first one is radio communication waveform, radio waves. Second one is microwaves. Third one is the infrared waves. Fourth one is visible rays. So ultraviolet rays, X-rays and gamma rays. So each and every spectrum waveforms have some frequency ranges. So that is mentioned here. Microwave means the frequency range 1 to 10 power minus 3. That's so infrared means 10 power minus 3, 10 power minus 6. Similarly, each and every waveform have some own frequency range and bandwidth. So here, so EM waves with long wavelength have low frequency. For radio wave and microwave have the wavelength will be long. So frequency will be less. So it contains a low amount of energy. So if you increase the frequency further, so it has the shorter wavelength and contains the high energy. So high frequency signals having high amount of energy. So these are the different types of waves available in the electromagnetic spectrums. So radio waves, microwave, infrared, visible, ultraviolet, X-ray and gamma rays. So this each and every range of frequency have some applications. So next we will discuss the different applications of electromagnetic spectrum. So first one is the radio waves. So it has the long wavelength, low frequency. So it is used in radio and television broadcasting. So it is used for the radio and television communications. So next one is microwave. So it is used in cooking, radar, the telephone and other signals. So we are using the microwave oven for cooking purpose, and also is a radar and telephone and other signals for the communication purpose. We are using the microwaves. So the third one is infrared waves. So transfer of heat from one place to another place or radiation emission depends upon the this infrared concept. So this it is used to transmit heat from one equipment to another equipment. So transfer the heat from sun, fires and radiators with the help of infrared signals. So next one is visible light. So with the help of this only we are able to see the different the colorings, different things. So makes things to able to see. So next one is ultraviolet. So ultraviolet is used to this is used to absorb the human skin, and also used that is applications used in the fluorescent tubes. So this is the UV light. So next one is X-ray. So it is used for the medical applications. It is used to view the inside body of and objects in the human body. So X-rays plays a very important role in medical applications. Next one is the gamma rays. So used in medicine for killing the cancer cells. So for the cancer treatment, gamma rays we are using. So each and every spectrum of waveforms having some applications. So next one is one different applications of electromagnetic principles. So it is used in radio frequency communications, that is RF communication, microwave engineering. We are using the microwave something. So microwave engineering. So antennas, that is mobile communication applications. So electrical machines. So it works under the electromagnetic principles. Satellite communication, atomic and nuclear research. So radar technology, remote sensing, quantum electronics, so VLSI technology. So these are the popular major applications of electromagnetic the principles or electromagnetic fields in our day-to-day life. So next, so we will go for the what are the sources and effects of electromagnetic fields. So sources of EMF. So EMF will be produced under the following equipments or process. So current carrying conductors produce the EMF. So whenever the changes in the current flowing through the conductor, it produces the magnetic field or electromagnetic fields. So mobile phones also produces the EMF. So radio, X-ray device, microwave oven, computer and television screen, high voltage power lines. So these are the sources of electromagnetic fields. So next, what are the effects of electromagnetic fields? So due to the EMF, so some effects also available. So it affects the growth of plant and animals. Also, it affects the growth of the human brain. Also, affect the performance of the electrical components. So due to the electromagnetic interference, so the performance of electrical components will be affected. So next, so we are going to explain the operation of the vector del operator with the three possible operations. So generally, we are going to represent the differential vector or del is called nabla or defined as. So del is called equal to del is equal to dou by dou x into ax plus dou by dou y into ay plus dou by dou z into az. So this is written by the in terms of Cartesian coordinate system. So ax, xy, z are the coordinates of Cartesian system. So this is the del operator. So based on this del operator, we have three concepts. One is a gradient. So gradient. Another one is curl. Third one is a divergence. So gradient means the gradient of any scalar function is the maximum space rate of change of that function. So maximum space rate of change of function is called gradient. For example, if you take the potential, that is scalar quantity voltage, there is electric potential is one of the scalar value, means we are going to take the gradient of this potential, mean that is called potential gradient. That is del V represent the potential gradient. So del V is called potential gradient, or that is called gradient of V, that is called grade V. So the formula for del V is equal to, so dou VV by dou x into AX plus dou V by dou y into AY plus dou V by dou Z into AZ. So here AX, AY, AZ is the unit vectors. So gradient of scalar is a vector. So if you take a gradient for any scalar value, means the output is vector. So this is called gradient operation. So next I'm going to discuss so divergence operation. So what is meant by so divergence? So this is another possible operation of divergence. So divergence of a vector A. So divergence, we are going to take divergence for the vector A. Divergence of vector A at any point is defined as the. So normal component of its surface. So normal component of its surface integrated for unit volume. So normal vector A with normal component. So normal component of the vector. So taken the surface integral which is equal to the volume enclosed by the surface. So del dot A is equal to, so limit volume tends to 0, limit volume tends to 0, 1 by volume into surface integral A dot n into ds. So surface integral, so of A dot n ds, so over the volume is called divergence. So we are going to write another formula for divergence. So if you know that del value, del is called dou by dou x into ax plus dou by dou y into ay plus dou by dou z into as. So this is the del operator. So if you want to take divergence means, so now take the dot product, that is scalar multiplication with the particular vector. So we are taking vector A is the vector means, so del dot A is called divergence. So del dot A. So if you take divergence, that is scalar multiplication between the del operator and A vector. So the final output is, so del dot A is equal to dou AX by dou X plus dou AY by dou Y plus dou AZ by dou Z. So this is called the operation divergence. This is called div A. So del dot A is called div A. So ax, ay, az is called the coefficient of the particular vector. So next one is curl of a vector. So curl of a vector A. So we are taking the vector A. So curl of vector A at any point is defined as the limits of its surface integral. Limits of its, so we are taking the surface integral, limits of its surface integral of the cross product with normal component. So A is the vector, we are taking the cross product with normal component. So n cross A, so is the cross product with normal component. So if you take the surface integral of this value, so that is called the curl. So curl of vector A at any point is defined as the limits of its surface integral of its curl of cross product with normal over a closed surface per unit volume. The volume sinks to 0. So expression is curl A is equal to limit volume tends to 0, 1 by volume, so double integral, that is surface integral n cross A into ds. So this is the curl operation. So generally we are going to express curl means del cross A. So del cross A, so we already know that del operator. So and also we taken the A vector. So ax into ax plus ay into ay plus az into az. From the Cartesian coordinate system we are considering A vector. So del cross means we need to take the curl operation. So we need to do the matrix operation. So del cross A is equal to, first row we need to write the unit matrix ax, ay, az. Second row we need to write the coefficients of the del operator, that is dou by dou x into ax, and dou by dou y into ay, and dou by dou z into az. So third row we need to write the coefficient of the A vector. So ax into ay into az. So if you take the determinant value of this del cross A, we get the curl value. So del cross A is called curl. So curl indicates a measure of tendency of a vector to rotate or twist. So it is a measure of the tendency of a vector to rotate or twist. So it is called curl operation. So based on the del vector, that is del operator, three possible operations are there. One is gradient. So del V is called gradient, potential gradient, one of the example for the gradient operation. So next one is divergence. So del dot A is called divergence. So curl operation, that is del cross A is called the curl operation. So this is the basic fundamental operations of the del operator. So next we are going to move the coordinate system. So basically three different coordinate systems are there. So one is the Cartesian coordinate system. So second one is a cylindrical coordinate system. Third one is spherical coordinate system. So for the different coordinate axes, each and every coordinate axis has a different coordinate axis. For Cartesian coordinate system, the coordinate axes are x, y, and z. A cylindrical coordinate axis rho phi z is the cylindrical coordinate axis. So next is spherical means r, theta, phi. So these are the coordinate axes of the different coordinate system. So first we will discuss Cartesian or rectangular coordinate system. So here, so coordinate axis x, y, z. So the three different coordinate axes are right angles to mutually right angle to each other. So each and everybody has a 90-degree phase difference. So right angles to each other. So with the help of this Cartesian coordinate system, we are going to represent a point in any region. So for example, we are going to measure the mention the point here. So this is available in with direction, some distance with a direction, ax direction, some distance from ay direction, some distance from az direction. So finally we are writing the position of the vector. So with the help of the Cartesian coordinate system, so a vector is equal to 2 into ax plus 4 into ay plus 3 into az. So 2, 4, 3 represent the magnitude magnitude of the vector. So ax, ay is that represent the unit direction of the vector, unit vectors. So next, so the differential surface of this Cartesian coordinate system. So if you increases the dx value, dy value, dx value for a small amount, finally we get this box, rectangular box. So it has three sides. So one is a dsx. So dx, dy, dz. So three different faces are there. So based on this, we are going to calculate the differential surface. So dsx is equal to dy dz ax. So dsy is equal to dx dz ay. dsz is equal to dx dy az. So differential length means, so the length between the 2 points of the diagonal distance. So dl is equal to dx ax plus dy ay plus dz as. So dx dy dz is the differential length increased for the x, y, and z direction. So volume surface means volume a component means dv is equal to written by dx. So dy into dz. If you multiply three sides of the rectangular box, so we are getting the volume integral dx dy dz. So this is the differential surface, differential volume, and differential length in Cartesian coordinate system or rectangular coordinate system. So next we are moving for the cylindrical coordinate system. So here three coordinate axes are rho, phi, z. So rho is the radial distance. So we are going to mention the point P for some distance from rho and some angle pi and some the height is that. So we are going to mention point here. So with the help of rho, phi, z, we are going to mention the points on cylindrical coordinate system. Here the differential length formula is equal to, so dl is equal to square root of d rho square plus rho into d phi square plus dz square. So this is the difference length formula for cylindrical coordinate system. So differential area. So ds means, so rho d phi into d rho, d phi into dz. So rho d phi into dz. So this is a formula for differential surface or differential area. So differential volume dv means rho d phi d rho dz. So this is the differential volume for cylindrical coordinate system. So third method is spherical coordinate system. So this is in the sphere shape. So in this we are going to represent the point P with the help of r, theta, phi. So r this radius, theta angle, and pi. So with the help of r, theta, phi, we are going to represent the point in the spherical coordinate system. So if you increase the small value of r, small value of theta, small value of d phi, finally we get the this type of box. So in this we are having the three sides. One is dr, another one is r d phi, third one is r sin theta d phi. From the three sides of the box, so we are able to get the differential surface and the differential volume formulas. So differential length in spherical coordinate system is equal to square root of dr square plus r d theta square plus r sin theta d phi square. So this is the differential length formula for our spherical coordinate system. So formula for differential surface, the common general formula is r square sin theta d phi. So r square sin theta d phi is the differential surface formula. So differential value means, so dv is equal to r square sin theta dr d theta d phi. So these are the three formula. One is the differential length, differential surface, and the differential volume. So we discussed the different coordinate system. So one is a Cartesian coordinate system or rectangular coordinate system. Second one is cylindrical coordinate system. Third one is spherical coordinate system. Next, I'm moving for the divergence theorem. So divergence theorem is used to convert the surface integral into volume integral. So it is using it to convert the surface integral into volume integral. So surface integral of d dot ds is equal to volume integral of del dot d into dv. So statements state that the integral of normal component of any vector field. So normal component of any vector field means d dot ds. So normal component of any vector field over a closed surface. So over a closed surface. So d dot ds over a closed surface is equal to the integral of the divergence of this vector field. So divergence, so del dot d is called divergence of the particular vector. So divergence of the particular vector. So again taking the volume integral for this combination, so that is equal. So surface integral d dot ds is equal to volume integral del dot d into dv. So we are going to convert the surface integral into volume integral. So this is called divergence theorem. So next one is Stokes theorem. So Stokes theorem used to convert this line integral into surface integral. Stokes theorem used to convert this line integral into surface integral. So integral h dot dl is equal to surface integral del cross h into ds. Surface integral del cross h into ds. So h is the field. So in line integral around a vector, that is line integral around a closed path, is equal to the surface integral of the normal component of its curl. So this operation is called curl operation. Del cross h is called curl operation. So line integral around a closed path is equal to the surface integral of the normal component of its curl over any closed surface. So left side is line integral. So integral, single integral, that is line integral, is going to convert into surface integral. This is the main function of the Stokes theorem. So next one is Coulomb's law. So it is under the electrostatics. So if you take the charges, two charges q1 and q2. So two charges are separated by a distance small r. So q1, so and q2 separated by a small distance r. So some forces will be appear between the two charges. So if the charges are equal, that is same charges mean repel each other. Opposite charge means attract each other. So this is the Coulomb's law. This is the Coulomb's law. So same charges attracts, same charges repel each other, opposite charges attract each other. So if the two charges are separated by a distance r, so it will experience some force. So it is depends on the along the line joining them. So directly proportional to the product of the charges. So q1 and q2 is the product of two charges. So and inversely proportional to the square of the distance between them. So r square. So f is, so force is directly proportional to the product of the two charges q1 and q2. So and inversely proportional to square of the distance r. So f directly proportional to q1 into q2 divided by r square. So this is the Coulomb law. So proportional constant can be replaced by the constant, means finally we get the formula. So force F is equal to q1 q2 by 4 pi epsilon naught into r square. So epsilon naught is called permittivity of the free space. R is the distance between the two conductors, so two charges. So Q1 and Q2 is the two charges. So this is the Coulomb's law. So next, so different types of charge distributions are available. So one is point charge. So it is your dimensionless point. So it is as a charge is q, that is point charge. So next one is the line charge. So if the charges are uniformly distributed over the length of the line means that is called line charge. So third one is surface charge. So if the charges are distributed evenly on the surface of the surface means that is called surface charge distribution. Third method is volume charge distribution. So that is called rho v. So point charge is called q. So line charge is called rho l. Surface charge is called rho s, and volume charge is called rho v. So these are the different charge distributions on the line, surface, and volume. So next, so basic definition. So what is mean by electric field intensity? So electric field intensity, that is capital E, is equal to F by Q, that is a force divided by charge. So electric field intensity, E is the force that a unit positive charge experiences when placed in an electric field. So if you place the charge Q in an electric field, so if you consider this is electric field E, so if you're going to place the charge Q in the particular electric field means it experiences some force. So electric field intensity means E equal to F by Q. That is force divided by charge is called electric field intensity. So we are going to write the electric field intensity in terms of forces. So already we derived the formula for Coulomb's law. So E equal to, from that formula, E equal to Q divided by 4 by epsilon naught into R square into AR. AR is called unit vector. So it's generally we are going to write. So electric field intensity is equal to Q divided by 4 pi epsilon naught into R square into AR. So R is the distance vector. So this is the definition of electric field intensity. E equal to F by Q, electric field intensity. So next, so we are going to discuss the Gauss law. This is one of the fundamental law in electrostatics. So Gauss law constitutes one of the fundamental law of electromagnetism. So it states that the total electric flux passing through any closed surface is equal to the total charge enclosed by that surface. So if you consider the surface, so this is the closed surface means the total flux passing through surface, total flux is called psi, total flux passing through surface is equal to total charge enclosed by that surface. That is psi is equal to Q enclosed. Psi is called electric flux. Q enclosed means enclosed charges on the particular closed surface. So this can be written as, so psi is equal to surface integral of d psi. So that's is equal to surface integral of d dot ds. So d is called electric flux density. So electric flux density, that is called field intensity or unit area. Electric flux density d is equal to epsilon e. So it can be written as integral d dot surface integral d dot ds. Similarly, it also going to write with the help of volume charge density. So Q is equal to volume integral rho v into dv. So psi is equal to Q is equal to integral surface integral d dot ds, that's equal to volume integral rho v dv. So this is the Gauss law. So psi is equal to Q enclosed. So this is the Gauss law. So next, so I'm moving to Biot-Savart law. So this is one of the important law in electromagnetism, that is magnetostatics. So it is used to determine the magnetic field intensity. So H is called magnetic field intensity. So B is called magnetic flux density. So it is used to determine the magnetic field intensity at any point. So it is called a Biot-Savart law. So we are going to consider this current element. So I is called current element. In that we are assuming a small element dl. So at a distance r from that current element, we are going to assume the point P. So the angle between the current element and the point P vector is theta. So the distance is r. So Biot-Savart law state that the differential magnetic field intensity, that is the DH, produced at a point P, so by the differential current element. So due to the differential current element at point P, DH will be produced. So this is proportional to the product of the line joining P. So it is the product of the element. So it is the product of the current element, that is IDL current element. So and a line joining P, that is sin theta, ideal sin theta, and is inversely proportional to square of the distance between R and P. Distance R between the P and the element. So electric field, that is sorry, magnetic field intensity produced at point P due to the current element DH is defined as DH directly proportional to ideal sin theta by R square. So product of current element and line joining to P and inversely proportional to square of the distance between the point P and the element. So DH directly proportional to ideal sin theta divided by R square. This is the Biot-Savart law, one of the important law which is used to determine the magnetic field intensity and magnetic flux density in magnetostatics for different conditions. Applications of Biot-Savart law. So Biot-Savart law so used to calculate the magnetic response even at atomic and molecular levels. So even at a small atomic and molecular level, it is used to calculate the magnetic response. So used in aerodynamic theory to calculate the velocity induced by vortex lines. So used to calculate the velocity induced by the vortex lines. So next one is importance of Biot-Savart law. So this is similar to the Coulomb's law in electrostatics. So the similar law is available in electrostatics. This is in magnetostatics. So Biot-Savart law almost similar to the electrostatics. So this law is applicable for very small conductors to which carry the current. It is applicable for very small conductors. So this law is also applicable for symmetrical current distribution conditions. So these are the applications and the importance of Biot-Savart law. So next one is Ampere circuit law. So Ampere circuit law, so it is relevant to the current. So magnetic field intensity around a closed path is equal to current enclosed by the path. So magnetic field intensity around a closed path. So that is integral S star dl. So magnetic field intensity is all H. So magnetic field intensity around a closed path, that is single line integral, is equal to the current enclosed by the path. So this is the magnetic field intensity enclosed by the line. So integral H dot dl is equal to I. This is the Ampere circuit law. So next one is the Lorentz force. So Lorentz force. So we are going to place a charge Q. So in the presence of electric field and a magnetic field. So this charge will experience some force. That force is called Lorentz force. So electric field develops one of the force against the this charge, that is electric force. So another one is magnetic force. Due to the magnetic field, another force will be created. So Fe is called force developed due to the electric field. So Fm is called force produced due to the magnetic field. So the combination of this electric force and magnetic field is called Lorentz force. So simply we are going to write the equation. So Q equal to E plus V cross B. So Q is called charge, E is called electric field intensity in that particular field. So V is called velocity of the charge. So B is called magnetic flux density. So Q into E plus V cross B. This is the Lorentz force equation. Force experienced by the charge in the presence of electric and magnetic field. For example, so this is the state of particle. So if the particle is in stationary means, so it produces only electric force produces only due to the electric field. So because the charges are in rest position, so electrostatic concept only available. So here force equal to F equal to QE, Q into E, that is charge into electric field. So here options of magnetic field is available. So there is no force, magnetic force. So finally we get the answer, same answer, F equal to QE. So next the particle is moving means, so in terms of electric field we experience the force QE. So in terms of magnetic field, we are going to experience, so Q into V cross B. So Q into V cross B, V is the velocity vector, B is the magnetic flux density. So if you, the combination of electric field and magnetic field available means, so finally the Lorentz force equation becomes F equal to Q into E plus V cross B. This is the Lorentz force equation. This is the Lorentz force equation. So next, so Newton's law. So when a magnetic field linked with a coil or circuit is changes in a manner, the EMF is induced in the circuit is proportional to rate of change of flux. So if suppose if the magnetic flux is linking in the circuit or coil, so if any changes in the magnetic field, so automatically EMF will be induced in that conductor or circuit. So the induced conductor EMF is the proportional to the rate of change of flux linkage. This within the circuit. This is called Newton's law. So EMF induced is proportional to the rate of change of flux linkage with the circuit. This is called Newton's law. So Lenz's law means, so the produced induced EMFs will oppose the rate of change of flux. So this is called Lenz's law. So these two laws combined together termed as Faraday's law of electromagnetic induction. So very important principle for the electrical machines. So DC machines works under the principle of electromagnetic induction. So Faraday's law of electromagnetic induction. So Newton's law and Lenz's law. Newton's law means the EMF is directly proportional to rate of change of flux. Lenz's law means the produced EMF is opposes the change of rate of change of flux. So combination of these two called the Faraday's law of electromagnetic induction. So this is the Faraday's law of electromagnetic induction. So induced EMF is equal to minus d phi by dt. So phi is called the flux. So the rate of change of flux, so is called the EMF. So negative sign indicates the, so rate of change of flux will oppose the EMF. So this is the Faraday's law. So if you use the n number of turns or n number of coils in the, that means, so formula modified EMF is equal to minus n into d phi by dt. So next, so we are moving for Maxwell equations. So very important concept for electromagnetic fields. So integral form of Maxwell equations depicts the underlying physical laws. So whereas differential form used for more frequently in solving the problems. For example, 4 differential Maxwell equations are there. So each and everybody derived from one particular physical law. So Maxwell equation is one is derived from the modified Ampere circuit law. So integral H dot dl is equal to I. So this is the Ampere circuit law. From the modified Ampere circuit law, so we are derived the Maxwell equation number 1. So Maxwell equation number 2 is based on the Faraday's law of electromagnetic induction. So EMF is equal to minus d phi by dt is called the Faraday's law of electromagnetic induction. So next one is third Maxwell equation is derived from the Gauss law of electrostatics, that is psi equal to q, that is the Gauss law of electrostatics. So fourth one, the derived from the Gauss law of magnetostatics. So that is phi is equal to 0. The flux around a closed path is equal to 0. So this is derived from the Gauss law for magnetostatics. So next we will discuss the Maxwell equations. So in integral form and differential form. So Maxwell equation number 1. So it is, so line integral H dot dl is equal to surface integral of j plus dou d by dou t into ds. So here j is called current density. So dou d by dou t is called displacement current density. So j is called conduction. J is called conduction current density. Dou d by dou t is called displacement current density. So in differential form, del cross H is equal to j plus dou d by dou t. This is the differential form. So next, so equation number 2. So it is belongs to the electric field. So integral E dot dl is equal to minus dou b by dou t into ds. So this is the derived from the rate of change of flux. That is the Faraday's law of electromagnetic induction. So in differential form, del cross E is equal to minus dou b by dou t. So Maxwell equation 3 is derived from Gauss law for electrostatics. So So surface integral d dot ds is equal to volume integral rho v dv. So surface integral is equal to volume integral. So differential form del dot d is equal to rho v. Rho v is called volume charge density. D is called magnetic electric flux density. So Maxwell equation number 4, integral b dot ds is equal to 0. So differential form del dot b is equal to 0. So this is the 4 different equations in integral form and differential form. So finally, so I'm going to conclude this session. So in this class, so we discussed more basic fundamental things in electromagnetic fields. So first we discussed what is meant by electromagnetic field and what is meant by electromagnetic waves. So what are the different waves in electromagnetic spectrum and its applications we discussed. So these are basic applications of electromagnetic principles. So sources and electromagnetic fields. So under different operations with del operator, 3 operator we discussed, gradient, divergence, curl, and we discussed the coordinate system, that is Cartesian coordinate system. The coordinate axes are x, y, z. Cylindrical coordinate system, coordinate axes are rho, phi, z. Spherical coordinate system r, theta, phi. And then we discussed the different basic fundamental theorems and the laws, that is the divergence theorem, which is used to convert the surface integral to volume integral. So surface integral d dot ds is equal to volume integral del dot d into dv. So next Stokes theorem, which is used to convert the line integral into surface integral. Integral h dot dl is equal to surface integral del cross h into ds. So next Coulomb's law, the force between the two charges is directly proportional to the product of the two charges q1 and q2 and inversely proportional to the distance between the 2 points. This is Coulomb's law. So next different charge distributions. So point charge, line charge, surface charge and volume charge distributions are available. Electric field intensity. So electric field intensity equal to F by Q, that is force divided by charge. Gauss law. So Gauss law is total electric flux passing through any closed surface is equal to total charge enclosed by the surface. So psi is equal to Q enclosed. This is the Gauss law. So next one is Biot-Savart law. So at point P, the magnetic field intensity due to the current element can be calculated with the help of this Biot-Savart law. So dH is directly proportional to ideal sin theta by r square. So Ampere circuital law. So Ampere circuital law means, so line integral of h dot dl is equal to I. Magnetic field intensity around a closed path is equal to current enclosed by that path. Ampere's law. So Lorentz force equation. So F due to the electric field and magnetic field, when charge is placed in the electromagnetic field means, so Q into E plus V cross B Newton. So we discussed the Faraday's law. So induced EMF is rate of change of is equal to rate of change of flux, and the negative sign indicates the induced EMF will oppose the rate of change of flux. So different Maxwell equation we discussed. So these are the 4 different Maxwell equations. So end of this session, definitely you will get some basic fundamental ideas of electromagnetic fields. Thank you.